this chapter, I'm going to talk about what mistakes will happen easily, what the consequences of those mistakes are, and how to avoid them. We will start with the classic buffer overflow example. Since its first officially documented misuse in a Morris worm, which led to an internet blackout in 1988, more than 3 decades have passed. However, a look into the latest list of common vulnerabilities and exposures, or CVE, reveals that buffer overflows are still a major threat as of today. Then I will introduce 2 free ebooks in which you can find practical examples and details for various programming languages regarding good coding practices, continued by some of the examples that are quite common. The chapter ends with a recap and an outlook about what is next. Are you ready? Let's get started. First, we have to define what a buffer is. A buffer is basically any sequential section of allocated memory. And if more data is stored than its allocated capacity allows, then we talk about a buffer overflow or also buffer overrun. An example for a buffer is a string in C, which is essentially an array of characters. In this case, the sequential memory section contains all characters plus, and that is important, the null terminator. Despite the string containing only 5 characters, we have to reserve 1 more character to store the null terminator, which indicates the end of the string. That is a standard in C, and hence we need 6 characters in total, a fact that is sometimes forgotten. How is a program structured once it is loaded into the RAM? It is divided into sections for various purposes, such as text for the program, data for initialized data, and BSS for uninitialized data. If that rings a bell, you are right. We had the same sections earlier in a session about the GNU compiler collection. The structure in the memory is comparable to the sections in the ELF file. For instance, like in the ELF file, the text section contains the binary representation of the program in the memory as well. Same with the BSS and the data sections. However, in addition, in the memory are additional sections for the heap and for the stack. The heap is memory space which is dynamically allocated. So if the developer reserves memory space using malloc or new, this heap grows upwards and it shrinks if the allocated space is released by using calls to free or delete. The stack is different when compared to the heap. Its purpose is to store function parameters, return values, and local variables used in the function itself. Every function call causes the stack to grow downwards towards the heap, and if a function exits, the stack shrinks. Please note that this memory organization is valid for Neumann processor architectures, in which the memory is used for both executable program code and for data. In contrast, the ATmega that we are using in this course is based on the so-called Harvard architecture, in which the program memory is physically separated from the data memory. In fact, this architecture enables the use of different technologies for each of the memories. In ATmega, read-only data and the program is stored in a flash, which retains its information even when powered off, while the variables, stack and heap are stored in the SRAM. Since a buffer overflow is independent of the used architecture, let's stick with the von Neumann for the time being, which allows us to demonstrate a buffer overflow on your PC. Let us do some magic and create a buffer overflow practically. For that, we have to understand what happens when a function is called. On the left is a demo program with a main and a function foo. Let's see what happens in an unoptimized version of the program. We know that there is a chance that the function is actually inlined or even removed, since it does not have any side effects. On the right is our RAM. We see that one of the addresses is marked as ESP, which is the current head of the stack. It points to the next available address in the stack and is therefore also called the stack pointer. Let's see what happens if the call to foo is executed. First, the values of the parameters given to foo are put on the stack. In this case, b equaling 6 is stored on the stack first, followed by the integer a, which is set to 5. When 6 and 5 are stored on the stack, automatically ESP is decremented and walks downwards to the lower addresses. In the next step, the return address is stored. This return address points to the next instruction after foo in the main. That is, it points to the instruction located in line 9. Next is the generation of the base pointer, or also called frame pointer. The base pointer is usually stored in a register in the CPU and simplifies the access to the value stored in the stack by dereferencing the base pointer with an offset. If you are patient with me for a minute, I will show what is meant by that. At the current address of the EBP, the address of the previous EBP is stored so that we can recover this address when we return from the function call. As a last step, the two local variables x and y are stored on the stack, pushing the stack pointer to the address 1FFC in hexadecimal format. As promised, what is the base pointer all about? Let's say we would like to access the value of x. How do we get that? The stack pointer already passed it and can change any time when, for instance, another function is called or the user puts something on the stack manually. We need a pointer that is constant and cannot change as long as the function is active. Here, the base pointer comes into play. The function foo adds a and b first and stores the sum in x. In assembly, it would look like in the listing below. First, b is loaded to a register called EAX. To obtain the value of b, the base pointer is dereferenced with an offset of 12 addresses. That means the address of EBP, which is 2008 plus 12, or C in hexadecimal, equals 2014, which is the address of B. Same with A, whose value is stored in register EDX. Then the values in EAX and EDX are added, and in line 4, the sum is stored at the position of EBP minus 4, which is the address of x. By now we know how the function call mechanism works. It is very similar when the local variable of the function is an array of characters. Instead of reserving stack memory for just 2 variables as in the previous example, here 12 spaces are allocated in total, 1 for each character. In the function, we have another function called strncpy, a function in libc, the standard library of C. This listing shows a simplified version of this function. Given 2 pointers, one for the source string and one for the destination, strncpy keeps copying from the source to the destination until a null terminator is found, exiting the loop immediately. Then the null terminator is added to the destination string as it does not have been copied yet, and the destination pointer is returned. So far so good. There's nothing wrong with this function except 2 problems. First, there is no fallback if the source string does not contain a null terminator. In that case, strncpy could probably copy large chunks of the memory till a null terminator is encountered by chance. And second, it does not check if the destination has enough memory reserved to handle the length of the source string. As you can see, The string buffer overflow has 16 characters, including the null terminator. Hence, there is no chance it will fit into an array with 12 spaces. So what is going to happen? Well, first the b is stored at buff0, right here. The u will be stored in buff1, and so on. In buff11, the f is going to be stored. But string copy will not stop here, since the f is not null. Hence, the L is stored at 200C, containing the ages to the previous EBP. This might not be dramatic in our case, since the previous EBP is not that important currently, since this is the first function call. It will be more severe if we are in nested function calls, since we lose access to the variables in those functions. However, the next character copy causes severe problems now, since the O is stored at the return address. When we want to return from the function, instead of jumping to the next instruction in the main, the CPU will jump to the address of the lowercase character O, which is 6F according to the ASCII table. Very unlikely, this is the address that we want to jump to. In lucky cases, the operating system recognizes this illegal jump and terminates this program with a segmentation fault. If not, or in absence of an operating system, the CPU will execute whatever data is stored at address 6F. That is the problem of von Neumann architectures. Data can be instructions, and instructions can be data, and we can just hope that the data stored at address 6F translates into an invalid instruction, causing an exception and a CPU stall. So let's see how that looks like. Don't worry in case we mess it up very badly. In the worst case, the operating system will complain about an inappropriate memory access and terminate our program. Very unlikely your PC is going to crash. Head over, open a terminal, and let's cause some segmentation faults. Welcome back to the buffer overflow demo. In this session, we are going to have a close look at what happens when a function is called. To have a detailed understanding, we will use the GNU Project Debugger, or GDB in short. I've prepared a short documentation with a list of GDB commands that we use in this lecture. It is attached to the resources folder. In the terminal, go to the indicated directory, that is course, mistakes, and stack string copy GDB example. In this directory, we have two files, makefile and strncpy.c. Let's have a look at what we are doing in this file, strncpy.c. I already opened it using VI. In this file, we have a function foo and a function main. In main, we call the function foo with abcd, and 1, 2, 3, plus the null terminator. So this string is 4 plus 3 plus 1 null terminator character long. That is 12 characters in total. In foo, we see that there is a buffer with 12 characters, so this string is going to fit. Then we copy S to the buffer and we print the buffer. Let's compile this program using the makefile. At the terminal, I just type in make and let it compile. You see, we use the G parameter to add debug information. This is important since it helps to make more sense of the GDB output. Once this is done, we can execute it, and as expected, the string is printed. The question is, what happens inside and how the function foo is called? invoke GDB with a program to be executed like this, and then this executable. To get to know what happens exactly at the function call, let's put some breakpoints where the program execution is paused. To do so, we use the command break with the line number. How do we know which line number? Having a look at our source code, you would like to have a breakpoint before and after this line is executed. So we set the breakpoint in line number 6 as indicated here, and one line later, which is then line number 7. Hence, break 6, and as a shortcut you can use B7, which is essentially the same. Now we have 2 breakpoints. Then run the program by executing the command run and wait till it hits the breakpoints. There we go. Breakpoint 1 interrupted the program for the time being. With the command info, various information can be read. In this case, let's have a look at the stack. So we type in info and stack. In this backtrace, we see that there are 2 frames on the stack. One belongs to the function foo with the given parameter s stored at this address and the string abcd 123 plus null. In this frame, the instruction pointer is in a function foo in the file strncpy.c and there in line number 6. The second frame on the stack tells us that we came from the main function in the same file. The function call to foo happened in line 11. In this main function, the instruction pointer is currently at this address. By the way, the addresses in this demo, such as this one and later more, might be different from the addresses that are printed in your terminal. This is normal. But we need more information about the stack. Hence, we type in info and frame, which automatically takes the first frame, that is frame number 0. Now, all important information is printed that belongs to the latest frame in the stack, that is frame 0, since it is a backtrace. So we see the current instruction pointer and a saved instruction pointer that probably points to the next instruction after the function call and where we return to once the function terminates. We also have the argument list with the pointer s, its content and its address. We also have the previous frame stack pointer and the base pointer at this address. The information such as the instruction pointer and the base pointer should be stored in the CPU in its registers. How could we display the content of these registers? Right, info registers. And here they are. Here's the base pointer, here's the stack pointer, and here is the instruction pointer. One note regarding the R in front of these registers names. You might have an E here or no character at all. The R indicates the size of the register. Have a look at this slide where I noted them down. If the register is RAX, we talk about a 64-bit register. If it's EAX, this register is 32-bit in size. Without any character in front of it, we talk about 16-bit wide registers, which is again divided into AH and AL for the higher and lower byte. back to our stack problem. Okay, so what is exactly on the stack? Since the stack grows downwards to the lower address, the values of interest must be at an address that is just greater of the current stack pointer. Therefore, let's print, let's say, the next few addresses from the stack pointer. To do so, we type X to tell GDB that we would like to display the memory content, followed by the /16x, indicating that we would like to print the next 16 elements in hexadecimal format. This is just an arbitrary number and might need to increase in case we would like to see more. And we would like to print starting from where? From the current stack pointer, which is a $RSP. And here it is. This is the address of the stack pointer. And as you can see, it increases as we go down. This is A0, B0, C0, D0. We have a lot of information here. Do we recognize anything in these hexadecimal numbers? Going through them one by one, we encounter, for instance, this address or this content and this content. However, continuing, we see that we have here 4 zeros and 4 fives, and here another 4 fives, and then 600 and D. And if I take this value and write it in front of this value, then I have the address of our function argument, string s. It seems that a pointer to the string is put on the stack. Then again we have something with 7 and triple F, which we currently do not recognize. We recognize this one though, which is the same as RBX and RCX. So these are also values on the stack. However, currently we don't know the purpose of those. Then we have plenty of zeros and some values which seem to be random, so we don't know what that is yet. Coming to the address of the current base pointer, which is this one, we expect the previous base pointer stored in this line somewhere. It seems that the previous base pointer, namely this address, concatenated with this address, is equal to the stack pointer of the previous frame. Currently, we are not in nested functions, since we just came from the main to the foo function. Therefore, the stack pointer and the base pointer of the previous frame are the same. What else is stored on the stack? Turns out that this one and this one represents the return address, namely the saved instruction pointer. Let's have a look at what is at this address. For that, we have to disassemble the main. So let's do that. The return pointer points to this address, which is phi1fe, which turns out to be this one. It seems that before returning from the main, the return value is put into EAX, which is a 32-bit register. Having a look at our source code, when we terminate main, we return 1, which is this one. So it's true that the return address points to the instruction after the function call. Okay, back to our function foo. Where is our local variable buff that is also somewhere on the stack? Let's investigate with the info command. So we type in info locals. That is the current content of the locals. It does not tell us much, since buff is not yet initialized. So it would be better to print its values in hexadecimal format. To do so, we type in p, hexadecimal format, and our variable name. As you can see, our buffer starts with 55, 55, followed by plenty of zeros. Looking at the content of the stack, we recognize this pattern here. Since buffer has a memory space of 12 characters and each of these elements is 4 bytes or 4 characters, we can assume that this is the memory space reserved for the local variable buffer. Let's have a look at it, and let's execute this string copy function. To continue to the second breakpoint, we can type continue or simply C. After the string copy function, you would expect this memory space to be filled with our string. Let's check if buff has changed by typing again in info locals. Our buffer changed from this string to this string, so it seems to have worked. And what happened to the stack? Let's print it again. As you can see, while everything stayed constant, this part has changed, and it seems that this is the space for our string. As you can see, the memory space now is filled with 41, 42, 43, 44, 61, 264, and 31, 32, 33, and the null character. What are these values here? Let's have a look at the ASCII table. This is the standard ASCII table. Let's have a look what 44 is. 44 is capital D, 43 is capital C, 42 capital B, 41 capital A. The lowercase characters A, B, C, D are starting from 61, and 1, 2, 3 is 31, 32, and 33. So the string ABCD 1, 2, 3 is stored at this memory location. What is the purpose of these fields here? It seems that these are padding fields and do not serve any purpose. Knowing how many padding fields we have, that brings us to the question, how long does a string given to the function foo need to be to crash the program? As long as the padding fields are overwritten, everything is fine. If the previous EBP is overwritten, that is fine too in our case, since we do not have any previous frame pointer as we just came from the main. Therefore, we need these 12 characters plus 1, 2, 3, 4, 4 into 4 characters, that is more than 28 characters, before we start overwriting the return address, most likely crashing our program. As a summary, if the string is between 12 and 20 characters long, the padding fields are overwritten. If it's more than 20 but less than 28, in addition to the padding fields, the previous EBP address is also overwritten, which is still okay in this case. However, if the string is between 28 and 36 characters, in addition to the padding fields and the previous EDP address, also the return address is overwritten. The second question is, can we use this buffer overflow to do evil stuff, such as calling a function that has not been called anywhere in the source. We just need the pointer to the function and place it exactly where the return address is. That's all for now. In the following exercise, I provided a program. Your task will be to execute the function attack without invoking it explicitly. Can you do that? We saw how to cause a buffer overflow in the previous session, but how to prevent such a buffer overflow potentially opening the door for attacks. First, do not use unsafe C library functions. Many of those have safe alternatives. For instance, for string copy, the alternative is strncpy, which allows to set the maximum length of characters to be copied in the count parameter, mitigating buffer overflows. There is also compiler support to introduce so-called canaries on the stack. A canary is a secret value stored in the first local variable immediately after the base pointer. Before the CPU returns from the function, it checks if the canary value is still there or if it has been overwritten. If the canary is different, then the program terminates. Otherwise, it returns and continues execution normally. The problem is that canaries must be secret, random, and generated at runtime. Otherwise, an attacker could disassemble the program and extract the canary. If the attacker wants to cause a buffer overflow, he has to make sure that the overflow overwrites the canary with the same value as before. In addition, since the stack is overwritten, the canary value cannot be checked against the value that is stored in the stack as well. Otherwise, an attacker could read the stack, extract the canary value, and overwrite the canary with the same value again, making it impossible to detect a buffer overflow and a possible manipulation of the return address. A solution to this problem could be to store the canary value on a heap instead. To do so, malloc or calloc need to be used. In ATmega, while malloc is available, it is quite costly to use. In addition, the problem with the randomness is still unsolved. Especially in small embedded systems, it is hard to find a seed that has a sufficient level of randomness. Therefore, some embedded systems rely on random generators implemented in dedicated hardware periphery. A developer always has to choose between effectiveness and efficiency. Later, more about that. This concludes the session about buffer overflow. In the next session, I would like to introduce you to two books or also wikis about C and C++ coding standards. In this short session, I would like to introduce two books to you. These books are free of cost. However, you have to register to download them. Fortunately, there's also a wiki that has the same content and you do not have to give any of your details to have a look at them. The first book is about rules how to develop safe, reliable, and secure systems. It shows many mistakes that a developer can make which lead to severe stability issues and long debug hours. The link is given here, and for the remainder of this chapter, I picked some cherries out of the book and present them in this lecture here. The other book is also about secure coding standards, however this time in C++, which has its own set of potential pitfalls. Apart from C and C++, coding standards exist for various other languages and scenarios such as Java, Perl, and Android. Have a look at the given link in case you have projects in those areas. For the remainder of this chapter, I picked out some of the most prominent rules. They are most about mistakes that I also did in the past. The purpose is to increase your sensitivity to potential problems in your code. Each of the following examples has a unique number, a 3-letter mnemonic for the section, followed by 2 digits to uniquely identify the respective rule. The suffix indicates the programming language. For instance, DCL30C describes a declaration problem, its number is 30, and it is regarding C. Therefore, in case you would like to have more information about this particular problem, just head over to the wiki and find the rule using the identifier that I always mention on top of the slides, or alternatively use the external link in the resources folder attached to the respective example. That's all for now. In the next few sessions, I will present some of the rules and show how it can be implemented better. In this session, we are having a look at the most common mistakes in C. Let's get started. First, rule DCL30C. This rule describes problems with objects and their storage durations. Every object has a storage duration which determines its lifetime. Throughout its lifetime, its storage and existence is guaranteed, and it retains the last stored value. In C, it is quite easy to access an object outside of its lifetime, maybe by chance. And the program might still work, however, it is not guaranteed to always work. So it might happen that the program works on one computer, but not on the other one, or it works 4 out of 5 times. Let's examine an example. What is the problem in this program? And if you found a problem, what is the solution? I suggest pausing the lecture here to study the given source code. Once you think you've spotted it, resume the lecture and I will discuss the problem and possible solutions. Okay, so what is the problem? First, we have a global pointer p here, and 2 functions, don't do this, already suggesting that here is something odd. And we have innocuous, which is very harmless. So what do we do in the function don't do this? We declare another string stored in C string, which is also a pointer. Then we equal C string and p and exit. The problem here is the different lifetime or storage duration of p and C string. Only within the function, C string's lifetime and validity is guaranteed. As soon as the CPU returns from the function, the pointer C string and the data on the stack could be destroyed and overwritten anytime. Its existence is not guaranteed beyond the function don't do this. Hence the data, which is expected to be printed, might be corrupted. Sometimes it will work, but it is not guaranteed, since the operating system or garbage collector might free that memory in any point in time. Maybe right before printf, or maybe after main terminates. Who knows? This causes undefined behavior. As a solution, there are 2 options. Either declaring a pointer with the same storage duration and assigning those values, or setting the global pointer to null just before exiting the function to make sure it cannot be misused. Both solutions seem to be undesired, as the value cannot be printed in neither of them. Hence, the implementation has to change fundamentally to provide the printing functionality of the string. Another classic example done often. What is the problem here? Please pause the lecture to think about it and a possible solution. Again, the problem is the lifetime of the variable array. Its automatic storage duration is only valid within this function. Nevertheless, the developer even returns a pointer which might become invalid very soon. A possible solution is to declare the array in the main and to use that pointer to initialize the array in the function. The lifetime of the variable array depends on the lifetime of main, and main is still running when the function call to init array is executed. Therefore, the pointer to the array is still valid in that function, since main has not terminated yet. This solution will also work for the previous example, in which the string is to be printed. Okay, that is the example for DCL30C. What else is problematic? In contrast to global variables, local ones are not initialized and can have any arbitrary value. We have seen this behavior in the buffer overflow example, in which the memory space was reserved for the buffer, but not initialized. In addition, function calls that reserve memory on the heap might not initialize that memory space either. For instance, malloc is one of those culprits, while calloc initializes and zeroes out the memory. Here is an example for that particular problem at hand. Have a look and think about what's wrong and how to fix it. Okay, so first of all, we have a local variable errorlog right here, which is initialized but then used in a sprintf function. Sprintf will interpret the values found at the pointer errorlog and will start copying till it encounters a null terminator, no matter if the remaining 17 slots of the buffer are filled or not. There might not be enough space in buffer to hold all these characters. In addition, why is there a pointer called msg given to the function but not used at all? It seems there is a bug here, and the original intention was to print the content of msg. There are two possibilities to solve the problem. In case sprintf is used for whatever reason, there is a safe version of sprintf available called snprintf, taking an additional parameter stating how many characters to be copied at maximum. In addition, it needs to be checked if the copy process was successful by checking the return value of snprintf, which equals the number of characters written to the buffer. It needs to be greater than 0 to be able to print anything. And the msg or message to be printed has been corrected as well. It seems that the developer overcomplicated the program a bit here. Instead of the string copying, it would have been sufficient to just printf the message. Okay, let's move on to the next example. Do not forget to check out the provided links for more information. Rule EXP34C is all about dereferencing null pointers. It is good coding practice to handle the memory management properly and not to rely on the compiler. For instance, if memory has been allocated on the heap using the malloc call, it is good code practice to free that memory space and set the pointer to null if it's not required any longer. Usually, accessing the value stored at the null pointer leads to undefined behavior, and in case an operating system is present, to segmentation faults. However, that behavior is not guaranteed. The null pointer is equal to an address pointing to the memory location 0. There are platforms which indeed can dereference that address and return its value, and hence the null pointer is valid. This shows an example. Have a look at the listing. What is wrong or even dangerous here? Have you found it? There are, in fact, several issues with the code. First, input string might be null, but we request for the string length in line 2 without checking that, so an error handling needs to be added. Okay, done. Now we are checking if input string is null and can react in case that happens. Second, malloc might return null if the memory allocation failed. We need another error handling here. Okay, error handling added for the malloc call. Issue number 3, we allocated memory for the C string. However, good coding practice states that we need to explicitly free everything that has been allocated. So a free C string should be done. In addition, we set C string to null. Contrary to belief, the function free does not set C string to null. It just deallocates the memory space. As a good measure, we set C string to null. This is actually not required in this case, since C string belongs to a frame on the stack which will be destroyed momentarily since we reached the end of the function. Let's illustrate another example regarding the function call to free. Let's say we add another pointer dstring and assign cstring to dstring after the allocation of memory, including the required checks. Then we free cstring and set cstring to null. This does not affect dstring, which is still not null. An example program is attached to the resource folder if you would like to try it out. As a summary, in C, the developer has the power to control the memory management, and with great powers comes great responsibility. So please keep in mind what memory is allocated, deallocated, and the state of pointers, alright? Okay, let's move on to the next example. Rule EXP42C discusses the comparison of structured data. Invisible to the developer, sometimes padding might be added to the elements of the struct as well as union. Here is an example. Imagine there is a structure and a function is needed to compare the content. The implementation is quite smart. Instead of comparing each of the elements of the structures, the memory blocks occupied by both structures are compared byte by byte. This has two advantages. First, even if elements are added to the structure, this comparison function is still going to work, since it adapts to the new size automatically. And two, it is more efficient to compare chunks of memory than accessing each element in the structures and compare them individually. Unfortunately, this comparison function might not work. The problem is that the compiler might add padding fields to the elements. The padding fields might be uninitialized, and the byte comparison will also compare those padding fields. This shows how the structure could be stored, including the padding fields, which are underlined. As you can see, despite the elements in the structures are all the same, the padding fields are not. Hence, a byte-wise memory comparison will return that both structures are different in this case. Therefore, an element-wise comparison is required. There is no such shortcut. Why padding in the first place? To explain this, let's consider the following program with two structures. The structures have identical members. However, the one on the right is packed. Therefore, executing the program shows differences in sizes. Why is that so? And what is the impact of this? For that, we have to understand a little bit about memory architectures. The memory has several I/O ports, such as the data bus, to read and write information. It also has a clock and control signals to tell the memory what to do, that is, for instance, reading or writing. In addition, there is an address bus indicating which memory address to access. Internally, the memory is organized in banks, splitting the data among them. This figure shows such an organization considering a 32-bit processor architecture, which can read and write 32 bits of data to the memory every clock cycle. To read data from the memory, the following steps are performed. First, set up the control signals so that the memory is informed that an address is to be read, and these links point towards the data bus. Second, put the desired address on the address bus. For instance, to read data from the fourth address from the bottom, the address bus will carry the value 0C. Third, clock the memory. After the clock, the data stored in the banks at the desired address will be available on the data bus. Every bank in the figure contributes 8 bits to the complete dataset. For instance, bank 0 takes care of the most significant byte, while bank 3 of the least significant one. Therefore, on the data bus, the data will be 00, 01, 02, and 03 in hexadecimal format. This method implies that with every clock cycle, 4 memory banks can be read simultaneously and 32 bits can be obtained at once. A similar sequence is applied when data is written. In this case, the control signals are set accordingly and the data bus carries the data to be written at the desired address. The padded structure S is stored in the memory as shown in this diagram. Fields in the memory marked with P are padding fields. The structure is to be read in this example. As you can see, the character CH is set to AA, while the integer I equals 1, 2, 3, 4, 5, 6, 7, 8 in hexadecimal format. If the character is to be read, address 0C is put on the address bus, and AA, including the padding fields, is then copied to the data bus. These padding fields are then discarded or at least ignored in the program, and all arithmetic operations are for the 8-bit operand. The value of the character, including the padding fields, are read in one clock cycle. If the integer is read, also one clock cycle is required to copy the data onto the data bus. However, in this case, it is a type of 4 bytes. Hence, the compiler will choose 32-bit operators for this value. When the same structure is packed, it will be stored in a pattern shown here. As in the previous unpacked example, the same method applies when the character is read from this structure. Instead of the padding fields, the first 3 bytes of the integer are copied along. However, they are ignored anyway. When the integer needs to be read from the memory, it becomes very different. First, the 3 significant bytes are read from address 0C. Since the memory copies 32-bit, the returned value will be AA 1, 2, 3, 4, 5, and 6. As you can see, the most significant bytes of this integer are at the wrong location. They need to be shifted to the left by 8 positions to obtain 1, 2, 3, 4, 5, 6, and 2 zeros. In a second memory access to 08, the least significant byte of the integer is read, together with unknown values, indicated by the X. But even this least significant byte is at the wrong location. It needs to be shifted by 24 places to the right to obtain 78. To obtain the original integer, these two values need to be concatenated or bitwise ORed. Compared to the padded structure, not only two memory accesses are required by now, but also two shifts and one OR operator are needed. While it is possible to compress the required memory size of structures, these savings in memory are paid for by an impact on the program performance, especially in architectures which are not able to read unaligned data from the memory without computation overhead. Even if an architecture can handle unaligned data, the memory still needs two reads, and the memory is usually a few magnitudes slower than the CPU. Please note, for the previous example, I assumed a 32 or 64-bit architecture. In case of the ATmega, the structure does not contain padding fields, as its SRAM only consists of one memory bank. To read a 4-byte value, such as a long, in total 4 memory accesses are required. As a summary, padding ensures fast computation but wastes memory spaces. Therefore, efforts can be undertaken to reduce the memory footprint. Consider the following two structures. The members of both structures are the same, just a bit jumbled up. However, this has an impact on the memory footprint. The sizes are different. The left one requires 16 bytes in total, the right one 4 bytes more. Why is that so? Let's have a look at how these structures are stored in the memory. First, the left one. Since the character member name is smaller than 32-bit, the remaining unused bytes or padding fields are utilized to store the following member C. The padding fields or values that are not used when reading the memory bank to retrieve the variable name are discarded in any case. However, in structure 2, this cannot be applied, since after name follows a type that requires 4 bytes in total. Hence, a new address is used for member ID2. This session gives just a short overview about how structures are stored in the memory. They are more complex, as it is suggested on first sight. We already discussed this in the buffer overflow section, but here is another example since it occurs so often. A developer has to make sure that the storage space is sufficient for the string, including the null terminator. Here is a function that can copy a character array. What do you think is the problem of this function, if there's one? Please pause the video here to give you time to think. Have you found it? Let's have a look at the loop iteration. Here, 4 characters are to be copied. The source string is Alex. In the loop, one after the other, the characters are copied. The loop exits once either null is encountered or I becomes greater or equal to n. After the x, I is 4. However, despite the fact that n is set to 4, an additional element is written to the destination which makes its length larger than n, namely 5. Therefore, it is required to remove one iteration from the loop and just let it run till I less than n-1. This error is also called off by 1 error, and it happens quite regularly. As we saw in the previous example EXP34C, the memory can be deallocated, but the pointer can still be valid. In this case, the pointer is called a dangling pointer, and accessing or writing to it leads to undefined behavior. Usually, a developer is aware of deallocated memory. However, accessing dangling pointers can happen unintentionally. Have a look at this listing. Is there a dangling pointer and where? If there's one, how to fix it? We are looking at the so-called linked list. The structure contains an integer and a pointer to the next element, which has the same structure again. So we get a chain of structures connected together by the pointer next. The pointer next of the very last element in that chain is set to null to indicate that there are no further elements. A pointer to the first element of that linked list is given to the function freeList. In it, the loop iterates through the structure and clears the elements. So it starts from the first element called head, and as long as p is not null, which means that there is no next element, the loop keeps iterating. So what happens here? We take the first element and store it in the pointer p. This p is then freed and its memory is deallocated. Then we go to the next element by setting p to the next element. However, for that we need the current p, otherwise we do not know what is next. But it has already been freed in the previous iteration. This is an access to a dangling pointer. Hence, before destroying p, we need to save the pointer to the next element here in Q, and then set p to that Q, solving the dangling pointer problem. Easy, right? It is just important to remember those details. Okay, another exercise. We have all used printf, scanf, etc. Those functions convert the values given as arguments, which could lead to severe vulnerabilities. A rather simple example is given here. What is the issue? The problem here is that the two parameters given to printf are swapped. Therefore, the variable arrow type is interpreted as a pointer and could potentially print out the string stored at the address until a null terminator is reached. The solution in this case is just to swap both parameters. Sometimes it is more convenient to use another programming language or even shell commands. Unfortunately, C has a function called system doing exactly that. It executes the command given to system in the shell or command prompt in Windows. Since the given command is executed in the shell, several attack scenarios are possible. The developer has to make sure that the command is sanitized and therefore not an arbitrary command can be given. But even then, what if the intended command in the shell is replaced by an executable provided by an attacker? Let's say ls or dir for Windows is executed in the system call to list the files. The shell will search for an executable going through the order given in the path. An attacker could add another directory to the path variable and execute another executable, which has been named ls or dir respectively. Here is an example. What could possibly go wrong? The issue is the tilde here, which indicates that the .config in the home directory is to be deleted. What defines the home directory? In the shell environment, this directory is set by the variable home. Obviously, it can be easily redefined using export, and suddenly the config in the root directory is deleted if sufficient writes are set. This is quite dangerous. So, what is a possible solution? To delete the file, libraries that are provided in C can be used. The script to do so is too long to show here, and I would like to refer you to the link given in the resources folder to have a look at the entire script. Many cryptographic functions require a random number as a so-called seed. An algorithm generates a sequence of random numbers based on that seed. If the seed is the same, so will be the sequence of numbers. Therefore, the generated numbers are not truly random, and hence those generators are also called pseudorandom number generators. As you can see, the quality of the randomness depends on the unpredictability of the seed. In a computer system which works logical, it can be challenging to find a seed. A seed can be generated based, for instance, on the time of the day, keyboard and mouse inputs, states of the CPU, operating system scheduler, and so on. However, in small embedded systems, many of those random inputs do not exist. For instance, in ATmega, a seed somewhere initialized after reset is very likely in a specific range, since many states of the system will be similar. Therefore, for a strong seed or randomness, random number generators implemented in dedicated hardware and attached to the embedded system need to be used. Curiously, Cloudflare installed a wall of lava lamps and a camera filming the wall. The video stream is then used to generate random numbers. A very aesthetic hardware implementation indeed. And another example. Have a look at this listing. What is wrong with it? Well, first of all, rand is never seeded. So the generated numbers of rand might always be in the same sequence. In addition, rand is very weak and hence should not be used in the first place. Here is a better way to generate random numbers. As you can see, the pseudo-random number generator is seeded by the current time of the day in seconds XORed within nanoseconds, right here. Obviously, there is a probability that somewhere the generator is initialized with the same seed. However, its chances should be fairly small. In addition, in the listing, rand has been replaced by random, which is stronger. But what if we do not have access to the current time of the day in, for instance, the ATmega? If weak randomness is sufficient in the ATmega, the ADC can be used to generate an initial seed by reading values from floating wires. The floating wires are not connected to anything and hence they catch electromagnetic radiation. Since the ADC can only read values between 0 and 1023, the randomness can be improved by cascading multiple readings. We will introduce ADCs a bit later in the course. The last example is likely to happen as soon as it comes to numbers represented by the type float. A float consists of a significand, a base, and an exponent. For instance, 1.2345 into 10 to the power of -4 is a float. The question is now, in a 32-bit float, how many bits do we reserve for the significand and how many bits for the exponent? The answer is, according to the standard for 32-bit floats, 23 bits are reserved for the significand plus 1 bit for its sign. The remaining 8 bits are assigned to the exponent. Since they are also signed, the exponent ranges from -126 to 127 with 2 numbers reserved. That means the radix point is floating and can move around based on the exponent as shown in the example. Hence, the name float. And for the CPU architects and hardware engineers among us, that is why floating point arithmetic is a lot more difficult to accomplish than integer arithmetics, as the exponents need to be synchronized first before 2 floats are ready to be used for computations. The problem with floats is that not all numbers can be represented. Let's explain with an example. Let's say the number 8,388,608 is to be represented in float. What we see here is a simplified binary representation of that float. We have the 8-bit exponent and the 24-bit significand with its sign bit. The number is positive, hence the sign bit is 0. 8,388,608 is exactly 2 to the power of 23. So the MSB of the significand is set, while all other bits are 0. Even the exponent is 0. Now we are counting up. The next natural number can be easily represented. We just increment the significand. We continue to do so until all the bits in the significand are set. This is then 16,777,215 or 2 to the power of 24 minus 1. For the next natural number, we cannot increment the significand any longer since all its bits are already set. Instead, we reset all its bits and increment the exponent by 1, shown here. However, if we increment the significand by 1 now, the next number is 16,777,218 and not 217, which cannot be represented any longer. A higher exponent decreased the precision of numbers, but now we can represent numbers that are beyond the maximum of 23 bits of the significand. This is also valid for rational numbers. Let's have a look where those missing numbers can cause a problem. Here is a simple loop that uses a float as an iterator. What could be the problem here? The problem could be that either 0.1 or 1.0 might not be representable as float, but only a close approximation. If, for instance, 0.1 is a bit less, the error keeps adding up, and instead of the expected 10 loop iterations, 11 of them are executed. How would you solve such a problem? A solution might be quite simple. Do not use floats as iterator, but derive them as needed in the loop as shown here. This loop will work no matter if the floats can be represented exactly or not. The same problem also occurs if the developer has to compare float numbers. Therefore, a comparison is always a check if the float is in a specific range with an acceptable error and not a comparison with a precise value. That's all what I have for you today. I believe that I picked some nice examples of mistakes that everybody did at one point in time or the other. A lot of those come with experience obtained through long debugging sessions. I'm hoping I could equip you with some shortcuts. Please do not hesitate and have a look at the other examples in the wiki which did not make it into this chapter. In this chapter, we did quite a bit. We started off with a buffer overflow and how easy it can occur. We had the buffer overflow in a function overwriting the return address on the stack. We also talked a little bit about countermeasures to mitigate the effects of such an overflow. To demonstrate what happens on the stack, we used a debugger called GDB. It allowed us to interrupt a program and to have a look at its state. GDB is very helpful and can also be used to pinpoint the notorious segmentation faults by executing the code, and once the fault occurs, to backtrack what led to it. Very helpful and faster than including printfs everywhere in the code. And for the majority of this chapter, we discussed examples and examples and examples. Many times, programming is a form of art, and there are many ways to solve a problem. To write good code, it requires experience, and experience is acquired by learning from mistakes not necessarily committed by you, but also by others. I am hoping this short chapter enriched your knowledge at least a little bit. And last but not least, what will be next? In the next chapter, we will discuss one of the most powerful periphery of the ATmega, the timers or counters. We will have a look at how, when, and for what to use them. So stay tuned, see you in a bit, and thanks for watching.